Welcome back. Today we're going to talk about section 2.1, which is linear and quadratic functions and modeling. The first thing we're going to do is look at our essential questions. We're going to look at what's a polynomial function. Can I make an equation and a graph of that equation? Can I rewrite an equation to make it easier to graph? Because we're going to look at the forms. What's a good regression? Can I apply a function to a given situation? So first of all, what's a polynomial? Well, a polynomial has a certain form. You'll be able to recognize it when you see it. I think the harder part sometimes is seeing what's not a polynomial. And so a polynomial has this form. It's some coefficient a sub n times x to some power. And then from there, the terms go down, and we continue to see this decreasing of the exponent numbers, okay? And so we get to a point where we have a sub 1 times x plus a sub 0, okay? That's a lot of math speak to say we've got coefficients, those a sub n's, they go with their terms, and the terms decrease in degree of polynomial. An example would be like 3x to the fourth plus 5x cubed plus 2x squared plus 4x plus 1. Okay, so that's got all of them, 4, 3, 2, 1, 0. So that's all of my exponents that would be from highest degree to lowest degree. But we can also interrupt the pattern and have something like this, 3x cubed plus 5, or like a 2x plus 6. This could be a negative 2x, whatever. Okay, so things that aren't polynomials don't follow that pattern. So it could be something like this. Okay, x is in the exponent. If x is in the exponent, it's not the base. So for a polynomial, the base needs to be x. Or we'd have like 15x to the minus 8. Well, a minus power, that's a no-no. Okay, we can't have a negative power because that gives me a fraction. Or we could have 5 times the square root of x. Okay, so that would be x to the power of a half, which is a problem because that's not what a polynomial is. Polynomial has integer exponents. So a polynomial of degree n means it has the highest degree exponent is n. So 3x cubed plus 5x squared plus 3 is degree 3, because that's the highest degree exponent. The leading coefficient is the coefficient of the highest degree term. So it's the coefficient of highest degree term. So for this one, the leading coefficient is 3 because that's the coefficient on the highest degree term. So when we look at polynomials, we're asking the question, is it a polynomial or not? So when I evaluate this, I've got 4x cubed minus 5x minus a half. Well, I don't see any radicals. I don't see any x's in the exponents. So this is, yes, this is a polynomial. So give the degree and the leading coefficient. So the degree is the highest degree. So that would be the 3. And the leading coefficient then would be the 4. Okay, so it's a polynomial of degree 3 with a leading coefficient of 4. In B, 6x to the minus 4 plus 7. No. Okay, this is no because it's got a negative exponent. H of x, let me draw this one in for you. This is what we're looking at in h of x. The big square root is 9x to the fourth plus 16x squared. Okay, so sometimes you're going to have to simplify these to see if it actually is an exponent. If it is a polynomial. But in this case, this is not, because this does not equal 3x squared plus 4x. Okay, you can't just take the square root of both terms. That doesn't work. Okay, it's not equal to that, so this is not a polynomial because it's got this big square root. In this one, I'm going to rewrite minus 2x to the fourth plus 15x. Standard form puts them in this decreasing degree of exponent. So the highest degree exponent goes first down to the lowest. And so this one is yes. Okay, I don't see any square roots. I don't see any x's in the exponents. And so my degree is 4, and my leading coefficient is negative 2. Okay? Here's some noteworthy polynomials. This is just information. If I have a zero function, f of x is equal to 0, its degree is undefined. It doesn't have an x. A constant function, f of x is equal to a, that would be like y equals 4. Well, the degree is 0 because it's essentially like 4 times x to the 0. Anything to the 0 power is 1, so it'd be like 4 times 1. If I got a linear function, which we're going to talk about, and quadratics we're going to talk about, this is a times x to the first power plus b. Well, that's where this comes from. Okay, and then obviously this is a squared for the quadratic, and so it's a degree 2. These are the noteworthy ones we're going to talk about. So when I look at finding a linear function, what they're going to give us is a little bit of different notation. In the past, we've said, hey, here's 2 points. Find an equation between that. Well, essentially what they're saying now is f of -1 is 2, and f of 2 is 3. We got to know what that means. As I told you, pre-calculus is a lot about the instructions and understanding what they mean. It's a lot of notation. And so if f of -1 is 2 and f of 2 is 3, that literally means this. Here's a point on the graph, and here's a point on the graph. So find an equation through these 2 points. Okay, so if I start out with point slope form, well, what do I need? I need a point, x1, y1, which I have 2 of them actually, and I need slope. So I'm going to find slope first. And I'm going to do 3 minus 2 over 2 minus a -1 is going to give me 1 over 3. Okay, so my slope between those 2 points is 1/3. So then I'm just going to plug and chug. So plug in a point. I'll pick this one. Y minus 2 equals 1/3 times x plus 1, because it's minus a -1. So I'm going to solve by adding 2 to both sides. So I've got y equals 1/3 x plus 1/3 plus 2. Well, this would be, if it's in thirds, it's going to be, sorry, this is in thirds, this is 1/3. And this one in thirds would be 6/3, right? Because it'd be times 2, 2 times 3 times over 3. So 1/3 x plus 7/3. Because this would be 1/3 plus 2/3, or 1/3 plus 6/3 would be 7/3. Okay, so that's my equation right there. Okay, so you got this here is an equation, or this here is an equation, depending on the form that they're asking for. Average rate of change. Now, as we get into some pre-calculus, we're talking about some pre-stuff, but so algebra 2, algebra 1, that was kind of a mixture of algebra 1 and algebra 2. We're going to move into some calculus terms as well. Average rate of change is huge in calculus, okay? But average rate of change just means in a linear function, it's the slope. The average rate of change is the slope, which represents our change in y over our change in x. Well, what does that mean? It means f of b minus f of a over b minus a, where a and b are these points where AB is on, where A and B are in the domain. Okay, so A and B are going to be things that go in. So, for example, let's say I've got, you know, a linear, a line here, and this is actually the constant rate of change theorem. But if I've got some A here and some B here, f of A is here, f of B is here. So to find the slope, it's the change in y over the change in x, which is, you know, obviously, if this is f of a up here, a comma f of a, and this is b comma f of b. Okay, those are the 2 points represented. To find that slope, you just take the two points and do the slope equation to them. The constant rate of change theorem says in a linear function, the slope is constant. Okay, the slope is constant. Well, think about that. If you've got a line here, the earliest way that we learned to graph was, okay, count out the slopes. So like up 2 over 1. Well, then you'd go up 2 over 1, up 2 over 1. And so it gives you a line because every slope is the same. Up 2 over 1, up 2 over 1, up 2 over 1. The slope has to remain the same because if it didn't, it wouldn't be a line. It'd be like, you know, all disjointed and all that. Okay? So when we talk about regression analysis is using points to make a line, okay? So it's using points to make a line. Typically, these are real life points, okay? So typically these are real life points. So for the purposes of this, I don't want to explain it in the video. You're going to need to come and talk to me about it, okay? But essentially, you're going to use these steps, okay? That's a lot of steps, which is why it's better in person. These steps to solve and use this data and those steps to come up with a regression, okay? So if you are in a boat where you're watching this for the first time and you're trying to learn this, come see me, okay? Come see me and I will talk to you about that. And so what comes out of this, though, is we have a correlation coefficient, R, and it tells us how close the data is to a line. Okay, so how close it is to a line is our R value, and that's one of the things that comes out up here. Like when we turn our diagnostics on, right here, diagnostics on, it's going to do diagnostics on the line, tell me, you know, how good of a line is this. Okay. What we're taking away from that example is this, though. Linear correlations come in all shapes and sizes, so your data is going to be sometimes, you know, we've dealt with a lot of things that are just straight in a line, okay? But sometimes the data is going to be a little bit off, above or below. And so if I see that data is closer to a line, it's going to have a strong positive linear correlation. Positive, meaning up and to the right. This one's a weak positive linear correlation, so generally it goes up and to the right. This one goes up and to the right a lot, very close to the line. This one is up and to the right, but kind of more spread out. This one is little or no linear correlation, okay? Because you see, as I go up and to the right, I've got some way out and way out. Not really helpful for making a line, that is. Could be very helpful if I'm trying to find a linear function. I could say it's not related. A negative correlation, okay? So negative means it goes down and to the right. This one is a weak negative linear correlation. Notice I don't put this down here because if it doesn't have a linear correlation positively and it doesn't have it negatively, it's kind of all in the same boat. So if it's all spread out, there's not really a linear correlation. Quadratic functions. Quadratic functions are particularly interesting because quadratic functions have this x squared property. And so we look at polynomials of degree 2, okay, and f of x is equal to, and this is our vertex form. It's going to be a times x minus h squared plus k, where hk is the vertex, okay, and like I said, this is vertex form. All right, and so what does this give me? Well, it actually gives me a couple of things, and what I'm going to do is I am going to put a parabola here, and I'm just going to kind of sketch one. This vertex is at h comma k, okay, wherever it happens to be. And there's a couple of things that we need to point out here. Where you split it down the middle, so this line through the vertex, so this is x equals h, okay, so it's the h coordinate, and this is known as the axis, or the axis of symmetry. Okay, if this parabola happened to open down like this, notice what happens. The axis is still the same. It's where I can fold it through the vertex. Okay, later we'll talk about parabolas that are on their side, but this is something that we need to understand. So this vertex form gives us a couple of things. It gives us very clearly the vertex and very clearly the axis of symmetry. And so everything that we are going to talk about now is with the goal of getting it into this vertex form. Okay, so we're going to do a couple of examples. We're going to transform the squaring function. So we take this squaring function and we're going to look at it in terms of, okay, I've got this vertex form. It tells me where the vertex is, but it's also related to translations. Because if you think about a regular parabola, and if it comes up from 0, 0, if I move it 2 and then 3, where did my vertex move? Well, it moved 2 and then 3. And so the vertex is tied to the translations very, very closely. Describe how to transform the graph of f of x is equal to x squared, that's our parent function, into the given graphs, give the vertex and axis of each, then sketch the graph. Okay, so a couple of things happen here. I've got 1, 2, 3 things that happen. So this 2 out front, got to remember what that does. It's a vertical stretch. By 2. When it's inside the parentheses and it's minus, it means right 2. And if it's plus 3 on the outside, that means up 3. Okay, so think about what this means for a minute. Let's just sketch our graph. At the very least, when I start out with my parabola at 0, 0, if I move it right 2 and then up 3, okay, where's my vertex? Well, my vertex is now at 2, 3 because my translations took it there. Okay, and so my vertex is at 2, 3. That means my axis, okay, so this would, in general, kind of go like this. So that means my axis is at x equals 2. It's the h value, okay, it's the h value. What does the sketch look like? Well, we can use points to kind of help ourselves out here. And so if I have 1, 1 is on my original parabola, well, if I'm vertically stretching that by 2, it means I go 1 and 2. So if I move that over to 1, 2, and up 1, 2, 3, kind of goes here, and it's symmetric. It's a vertical stretch by 2. So it takes it and makes it half as wide because it's stretching it by a factor of 2. In this next one, let's look. A couple of things happen. I've got this little negative out front, I've got the half, and I've got the 3. The first thing that I'm going to do is I am going to vertical stretch by a half. Okay. The second thing I'm going to do is flip over x. Okay, because it's easier to do it like that than to flip it and then stretch it and flip. And then the third thing I'm going to do is go up 3. So where's my vertex? Let's just take a look. Well, my vertical stretch by a half and my flip over x don't do anything to my point. The up 3, that does something to my point. Okay, and so 0, 0 is my vertex. If I vertical stretch it, it doesn't go anywhere. If I flip it over x, it doesn't go anywhere. Then I go up 3. So all of a sudden now I'm at 0, 3. That's my vertex. So my axis is x equals 0. Okay, now what does it do? Well, it vertically stretched by a half. Sorry, shrink. You guys are out there like, what? Vertical shrink by a half. Vertical stretch by a half really just means you stretch it by less than 1. So it's stretched by a half, so it would be like this. So it's essentially a shrink. That's why I said that. So it's a shrink by a half, which means that everything is half as big as it was. So instead of going to 1, 1, it went to 1, a half, 1, a half. And when it gets flipped over x, it goes here and here. And then I move it up 3, it's going to be here. So instead of being skinny like this, it's actually going to be super wide like this. Sketching by hand is important, but not as important as understanding where the vertex moves. Okay, so that's why I did the graphs really quickly. A couple more things here. We're going to rewrite the equation. The directions in your homework are going to ask you to rewrite the equation, and our goal is to get into vertex form. Okay, so get to vertex form. This is not in vertex form. The other tricky part about this is I'm going to be completing the square, but I can only work with one side. This is not an equation like we've done in the past with completing the square. I don't have a 0 equals, and so I have to work with one side. Must work with one side. okay? And so I'm going to have to kind of do the principle of completing the square without doing all the division and having two sides to work with. So the first thing I'm going to do, I still want a leading coefficient of 1. And so I'm going to factor out of 4 like this. Okay, I factored out of 4 because now I'm just going to work with this part here. Okay, I'm just going to work with this part here. And when I do that, I'm going to complete the square in here. So I've got x squared minus 3x plus something plus 2. And you're like, Mr. Seris, but usually I'm working with sides. I can't change the equation. Okay, so if I add something in here, I need to subtract the same thing. And you're like, well, that doesn't make any sense. Well, I'm manipulating the equation to get a perfect square plus something. What goes in there is my b over 2 squared. Minus 3 over 2 squared plus 2 minus 3 over 2 squared. Okay? And so essentially what we're doing here is we are adding negative 3 over 2 squared and subtracting negative 3 over 2 squared. Still not equal to anything. So it's still standing on its own. And so when I do a little bit of simplification, I've got this negative 4, and in my brackets, this is now a perfect square, right? And so inside my brackets here, I've got x minus 3 over 2 squared plus 2 minus, and then this 3 over 2, negative 3 over 2 squared is minus 9/4. Okay, so negative 3 over 2 squared would be 9/4, so minus 9/4. When I simplify this, I've got minus 4 times x minus 3 halves squared. And so if I do a little bit of math here, this is 8 over 4, which is 2 minus 9 over 4. So this is minus 1/4. And now what I'm going to do is I'm trying to get this to a form where I can have vertex form. So a times x minus h squared plus k. And so I'm actually going to distribute this 4 in, and you're going to see what happens here. So I've got negative 4 times x minus 3 over 2 squared. And then minus 4 times 1/4 would be plus 1. So check it out. A times x minus h squared plus k. So my vertex is at 3 halves, comma 1. And my axis is at x equals 3 halves. Okay? And so this becomes very simple to see exactly what I'm looking at, where my vertex is, where my axis is. I had to do a little pre-work on the front end. Okay? Let's try one more. So pause it here, try this one. After you come back, I'm going to do some explanation. So I'm just going to keep going, but you can pause and try it, and then when you come back, it'll be ready to go. Here we go. So I'm going to factor out of 3. This one's a little bit different right here, right? Because what I just did was I should have x squared plus 4x plus 11/3 in my brackets. And so when I factored out of 3, this became 11/3 because 3 times 11/3 would be 11. So I'm going to add 4x plus, this is going to be 2 squared, plus 11/3 minus 2 squared. If I do some simplification, I've got 3 times x plus 2 squared, plus 11/3 minus 4, because 2 squared is 4. If I hop this up here, draw myself a little line. I've got 3 times x plus 2 squared plus 11/3 minus 12/3, right? And so this becomes 3, I'll do the in-between step, minus 1/3. 11/3 minus 12/3 is minus 1/3. And so when I distribute this 3 in, I've got 3 times x plus 2 squared minus 1, because 3 times 1/3 would be 1, so minus 1. So my vertex is at negative 2, comma negative 1. And my axis is at x equals negative 2. Okay? So putting that in vertex form helps me find the vertex and find the axis. I had to do a little bit of that work there to get it done. Here's another way to do it. So if I excuse me, if I look at this example, I want to find the vertex and axis of the graph of the function 6x minus 3x squared minus 5 by rewriting the equation for the function in vertex form. I'm going to show you a different way to do this. My vertex is that x is equal to negative b over 2a. There's another way to do this. So you could write it in vertex form, which works perfectly. Okay. There's a little bit of work to do that quadratic, that completing the square, but you get, on the other end, you get the vertex out. Another way to do it is to look at the coefficients, and the coefficients and the vertex are very closely related in that the x-coordinate is the coefficient negative b over 2a, and y equals f of negative b over 2a. And so when I've got an equation like this, all I need to do is rewrite. F of x is equal to negative 3x squared. I'm writing it in standard form with my exponents decreasing so that I can discern what a, b, and c are, plus 6x minus 5. And so my a, b, and c are here. So my vertex is at negative b over 2a, comma, f of negative b over 2a. And so that means that if I take negative b, that'd be negative 6 over 2 times negative 3, comma, f of negative 6 over 2 times negative 3. So this is negative 6 over negative 6, so 1, comma, f of 1. And I'm kind of delaying this here, not on purpose, but just kind of giving you every step. And so f of 1 would be negative 3 times 1 squared plus 6 times 1 minus 5. So it's 1, so negative 3 plus 6 minus 5. 6 minus 5 is 1, and negative 3 plus 1 would be negative 2. And so this is at 1, negative 2. So what's my function? I want to rewrite the function in vertex form, so I can do it like this. I could say, so use all this information, everything I just made here, can go this way. F of x is equal to, my a is negative 3. Negative 3 times x. My vertex is 1, 2, so x minus 1 squared plus a negative 2. That's my vertex form. Whoops. Okay, so f of x is negative 3 times x minus 1 squared minus 2. So my vertex is at, scroll down here, 1 comma negative 2, and my axis is at x equals 1. Okay, so that's another way to do it, is to take the coefficients and do negative b over 2a for my x-coordinate, and then do f of negative b over 2a to get my y-coordinate of my parabola. My vertex, my parabola. Last one. Thanks for sticking it out. Hopefully this is helpful. Another way to do it would be to be given the vertex and a point and to have to write an equation. The best way to do this is to start with the equation. F of x is equal to a times x minus h squared plus k. And so I have to look at what I've got. Well, notice, they've given me h and k, right? So I've got that. And then this right here is an xy pair. Well, really it can be written like this. X and f of x, right? So if I look at this equation that I've got, I have 1, 2, 3, 4, 5 variables. But in the equation, in the problem, they actually gave me 4 of them. And so if I simply fill in all the blanks, f of x is 2 is equal to a I don't have, and then x minus h squared plus k, which is negative 10. If I do a little bit of simplification, x is equal to, so 2 is equal to a times 2 squared minus 10. If I add 10 to both sides, I've got 12 is equal to 4a. So therefore, a is equal to 3. And so then I'm going to write an equation using those pieces that I just found out. So my equation has to be f of x is equal to a times x minus h plus k. So I had a plus 1 because x minus a negative 1, and then plus k would be minus 10. This is my equation right here using my a that I found from plugging in all of my information. Okay, guys, that's all there is to it. Thanks for watching, and we'll see you next time.